get started. So we keep recording, and would like to have a 10 project presentation number one, and I'd like to have everybody to have present to demonstrate your program about the final experiment. Yeah, you might go on. 来，一群开始吧。
你这样听得到吗？
可能要再大声一点。等一下。
好，这样呢？
还是很小声，不知道为什么。
还是很小声。
现在这样还可以，不知道为什么。你是不是距离太远，还是你戴耳机？
哦，没有，老师，因为我那个本身的电脑进不去，所以我只能用2个装置用。
你的电脑进不去，为什么？看一下，好吧，开始吧。
好。这个漏斗实验，那一开始那个 ID 的部分就是一开始就是漏斗实验里面的 ρ1 是YK 会等于随机乱数 1K， 那这个是我的实验结果，那就可以看得到说，
你可以现在现场 run 吗？
什么？
可以现场 run 你的程式吗？
好。等一下，看，这样有看到吗？
可以啊，开始。你自己设吧。
这样。
output bin。好，但是不一样弱。
不一样弱。这个是 ρ2。
厉害啊！这是 ρ2 对不对？这是 ρ2。那你再 run 一下 ρ1 看一下。那为什么 sigma 没什么改变呢？你看一下 ρ2 你的 sigma 来看一下，还是
这个？
对啊，应该是它的1.4倍啊。
1.4倍。
来，你 run 啊，对不对？我们上课是不是应该是它的1.4倍？老师上课有没有讲过？有吧？
有。
它的变异数是它2倍，所以说它的标准差是它的 ρ1 的1.414啊，对吧？你这有问题，对，这有问题。
好，
看一下 ρ3。
我觉得应该是我没有改到，
我不知道，你自己去检查。来看一下 ρ4。那好，那你改完，你下个礼拜再报告好。来，下一位。
好。
来 看下位要谁？志宏好了。
这样有看到我的画面吗？
等一下哦。
要先讲 PPT 还是先跑程式？
先跑程式再讲 PPT 吧。
好，那这样看到吗？
可以啊。
好，那这个是 IID 的部分。好，这个是 IID 的部分，然后这是 Rule One。
等一下我看一下，0.9变异数0.97。9987变0.97多。哦，你那个变数把它变1000，看会怎么样？你上限是多少？不是你的那个数目行名不？你的上限是多少？500还是1000？
我没有设定上限，可以
那
改。
那你设1000看会怎样？跑出来吗？还在跑？
还在跑。
这东西那么简单，怎么要跑那么久？好，这是0.9695。你的荧幕型打大一点，有点小，我看一下全荧幕。
打大一点吗？
好，可以了，来，我看到了，没关系，我看到了，来，然后
这样子有比较好吗？
有，再跑 Rule 2来，0.01993。超过1.4这就对了，因为它的这个就对了，有没有看到它的变异数是原来变异数的差不多2倍，对不对？因为我 run 的这个 number of simulation 越多，它越会是接近它的2倍，这样，然后再看 Rule 3。
好。
OK， 好，不要1000把它改成100好了 ，run 太久了，没有必要，我们要看趋势 ，run 换500就好了，run 500，500对500，好，Rule 4对。你可以看到它的变异数也不固定，对不起，平均数也不固定，变异数也是变得很大。好，那这个，你换到 Scenario 2，
好，
有那个 Auto Correlation 对。
等我一下哦，都跑到那。
哎，那个各位同学，明天要开始回学校上课，知不知道
知道。
？Hello，知不知道？等一下，我看哈，500，你 Phi 用0.9，可以，好，Phi 用0.9，大概变异数是5.98。好，你用，等一下，它应该有2个 sigma 吧？不对，它有2个，一个是 epsilon，一个是我看一下，一个是它用paper 中间一个是 EA，一个是什么？
EA 一个是 EK 是吗？
一个 EK 一个 EA 嘛，那你这里
我应
是
该要设2个那个 mu 跟 sigma。
没有，你 sigma 你的 sigma 是这里是什么的 sigma？
我让两个都用同一组 mu 跟 sigma。
你说 scenario one 跟 scenario two 都用同一个 mu 跟 sigma， 我能理解，但是在 scenario two 不是，它中间有两个随机，一个是1k，一个是一个是我看它有两个那个 white noise 白色杂讯的，对不对？一个是在 eta 里面的，一个是 EA，一个是 ET， 是不是？不看。
1k 跟
1k 跟在原来的第一个模式里面是 1k 嘛，然后在 eta t 里面的是叫做
AK
AK，所以说你要有两个 sigma， 因为你要去做那个 table 出来，是不是也要需要两个 sigma？
我是设两个，但是我在输入这边我是拿
什么？
都是设同一组的 mu 跟 sigma。
第二组不需要 mu 啊，就是 eta t 里面没有 mu 啊。eta t 里面有 mu 吗？它只有 y 等于 mu 加上 1k 再加上 eta k 嘛，对不对 ？eta k 又等于又等于 ak 再加上 phi eta k 减1啊。最后你的 table， 你再去还原文章中间的 table， 不是要输入两组不一样的 white noise 嘛，对不对？那你在这里为什么只有一个？你到底听得懂听不懂我讲啊？
我有听懂。
那这里为什么只有一个？
我再回去修改好了。
好，没关系，你把它让 Word to 我看一下。
好。
2点多5点多。对啊，你可以看哦，到 Raw 2的时候，它就表现的比 Raw 1好，代表我的那个 auto correlation 很高的时候，对不对？我们看一下 Raw 3。Raw 3。OK， Raw 4。它应该也是发散的。怎么没有图啊？
要等一下，老师，他可能有点。哦，有了。
哦，这个图就很奇怪，怎么会长这样 ？Raw 4 OK，Raw 4是 Random Walk 是 Raw 3还是 Raw 4？
Random Walk 是
哪一个 Raw 是 Random Walk？
Raw 4。
Raw 4。
哦，这个是要可以让，所以说，所以说，那你在 create， 那你在写你报告，你说你在还原那个文章中间的 table， 那你是有一个是 1k， 一个是 ak， 你有设两个吗？还是只设一个？
1k。
你还是没有听懂我讲的。你现在手边有没有文章？
有。
你把它拿出来看，快点。对，你们现在是在那个志荣，你在台中还是在台北住的地方？在台中。
我在台中。
OK， 你们知道明天要回来对不对？
知道。
好，来，你把它文章打到最前，来停一下啊，来不要动。你看一下你的 YK， 看公式吧。你是不是 YK 等于不要看这个，来往前走，往前走，再往前走，快点。好，停。看公式6。
16。
公式6。来看这边是不是一个 AK， 对吧？然后这是第2个随机变数，对不对？你再往前走，公式1还是公式，再往到公式5好了。好，停。你这边是不是有个 EK？EK 是原来 YK 的什么？的这个随机乱数，就是它的那个 Y sequence Y noise， 对不对？所以它有2个啊。那它的平均数都是0没有问题，但是它变异数有可能一样，有可能不一样啊。
懂。
好，那你再回到那个要你们还原的 table 那里来。来，停。再往下走一点，好，停。这边它不是有 rule 1 rule 2 for various， 这边有 sigma E 跟 sigma Y， 对吧？还有一个比例，我看到，你有没有看到它的 table 的 caption 有吧？
有。
那你中间会给到 sigma A 的话，就是那个第2个随机变数嘛，对不对？第2个 Y noise， 还有一个 sigma Y。你 sigma y 的平方，它基本上你可以看在公式9中间有2个，一个是 sigma a， 一个是 sigma e 嘛，所以还是需要2个，你才有 sigma y 嘛，对不对？所以说你一定要2个，你才能算出这个比值，才能还原出原来的这些 table 嘛。
了解。
好，懂了吧？
懂。
好，来，你们自己回去改哦，然后再来小白兔换你。
老师，我可以问个问题？
问啊。
就是请问一下，那个 table 不是直接用那个 equation 的值去做出来吗？
没有啊，我用公式可以算得出来，没有错啊，那是理论值啊。现在我只是想要用你们的程式去确认啊。
可是那我们要怎么？其实我有点不懂，是我们要怎么样去做到 sigma 1的平方除以 sigma y 的平方正好等于0.1、0.25、0.5跟1呀？1可以啦，我不知道怎么样去做成那个 sigma y 1的平方除以 sigma y 的平方等于0.1。
没有，你就是要去设 sigma 1跟 sigma a 的数值啊，然后你在那个我们刚刚不是有看到文章吗？
对，
它中间有 sigma y 跟 sigma e， 你就用那2个公式去确认 sigma a 跟 sigma e 的数量要多少，可以让这个比例接近那个比例啊。然后设完以后，你就用程式去跑，懂意思吗？
跑完之后就直接把 variance YK 如果
2对，然后用你的结果去印证你的 table， 你的 table 就是用程式跑出来的结果。
好，我懂了，OK， 好。
有没有听懂啊？啊，
好，我懂了。
OK， 好，再下一位，那个再来小白兔好了。
老师，我的 table 2也是刚才懂。
哦，好了好了，那现在
那我要跑程式吗？
哦，我看一下你的程式好了，我看你到底有没有偷懒来。你run 一下程式，对。哦，所以说你只有一个 scenario， 哦，你有2个 scenario，
2个
，2个，好啊。
这是 IID 的。
让我看一下哦。 0.1 0.9，好，那 raw 2。哦，差不多，这数值就对了。raw 3，来，raw 3，可以 raw 4，看这个趋势对还是不对，这样比较重要。哎，你的荧幕可以大一点吗，小白兔？
这个已经是最大了。
真的哦，好，对不起。
哎，等一下我看一下，这样有比较好吗？
好了，好，没关系。然后你到 scenario 1，scenario 2，对不起，你这里也是只有设一个 sigma，
对，
为什么？你为什么？
就是都是用平均数是0，然后标准差是1。
那我刚是不是有讲，是不是有一个是 EK，一个是 AK？你知道那是？那
我知道。
你现在知道了吗？
我知道。
好，没关系，你还是 run 一下，用 n 等于500看看。那个大白兔，你有没有大白兔，你有没有听到老师刚讲，你也是这样做吗？有设2个 white noise。于晴，
有，
你是这样做吗？你不是这样做吧？
不是，
好吧，那你
跟安婷他们一样。
你们都错一样了，好，没关系，你们自己再去改啊。来看一下，0.9，0.9 ，OK， 500，
是这个，
对，好，我知道，这边负0.2 min 6点多，好，看一下 raw 2，这趋势大概就没有问题了。你可以看它 variance 就变小，对不对？对啊。你不，等一下，再 run 一次，再按一次，对，再按一次。variance 又变大，然后再回到再 run raw 1一次，variance 6点多。这有点怪你 raw 1的 variance 4点多，你 raw 2竟然比它大，然后你再按一次 raw 2。小白兔，你这个可能有问题哦。你看你这个 variance 比人家大，所以你的 raw 2有问题，不是，就是说你的有 auto correlation 的时候，这有问题。你有看到问题吗？
有的时候 raw 2大，有的时候比 raw 1小。
可是这个就是那个什么 EA， 你通常你的 phi 0.9已经够大，你不然你是0.95，来是0.95，这种一定是没有什么好讲。先按 raw 1，应该就已经那么大了，应该 raw 2一定会比 raw 1要来得好。
等一下，我这宕机了。
就是你的程式还是有点问题，对啊，怪怪的。所以说你要按照那个 table，它有一个界限，那个 sigma y 跟 sigma E 的比例，然后 auto correlation 在什么范围之内，它就会 raw 2比 raw 1要来得好。你宕机了。
对。
出来了，这是
raw 1。
raw 1，你看这是7点多，对不对？它跟人讲，来你看一下 raw 2。这城市那么小，为什么应该6点多？应该不，你这里有点问题哦，你可能要再去检查，好不好？
好。
检查好，再来换那个折成。
老师，我那个目前也是 Table 2那边有点问题，但刚才听过老师讲解之后，又比较懂了。那这边看得到吗？
对啊，你就重新 run 开始。
程式。
你也一样是用一组 white noise 还是2组 white noise？
我是用一组。
你们为什么会认为可以使用一组？我想要了解你们当初的想法。明明 paper 不是写2个。哲成，我们讨论一下啦。
好
paper， 而且老师上课是不是讲2个？
对，好像讲到 sigma A 跟 sigma E， 就是
对啊
AK 跟 EK。
对啊，我明明上课讲2个，为什么你们要做1个？啊？为什么？你跟我讲一下理由，你给我一个理由就好了，我也不会骂人。
因为我想说放一样的看看可不可以跑出来，先跑出来这样。因为那时候在改的时候一直有 bug。
程式里面，好，我先不管你是输入，就是说，那你程式是里面是一个 white noise 还是2个 white noise？ 你真正的程式里面，
这2个只是都是用同一个 sigma。
哦 ，OK， 好。
对，那我先跑 raw one 的部分。等一下哦。
你的统计量在哪里？
我重跑。对，老师，那个我的统计量昨天在修程式的时候，它有点 bug， 所以可能要从这边看。
猪头啦，哪有人家这样在那边看的啦？
怎么？
那你跑不出来，你要不要去问那些3个女生她们怎么弄的？你们总是要交流一下啊！你们不要每一个人都是一个孤岛，好像大家都形同陌路。
刚才还跑得出来。
你们有问题，你们可以互相交流，又不是说研究所不是大学生大学生就是那种我考古题我不要给你看，研究所不是这样啊。研究所怎么是这样？大家就是尽量我知道的全部告诉你，你知道的全部告诉我，这才叫研究生啊。你们所有的研究生有没有听到？你们要乐于分享，而不是说啊，我今天知道我不告诉你，我考古题不让你知道，这个我跟你讲，这会害死你自己啊。研究生不是这样当的，不是说哦，我今天我知道了，我尽量都不要告诉你。在研究生的这本分就是尽量去分享，然后别人知道了才会分享给你嘛。哦，你们真的是头坏掉了，真的是都自己一个人当做孤岛躲起来做，这样怎么会进步？笨的要死！来 run 吧，不要再
这是ED 的图，然后统计量在这边。
在哪里？
在这边。
出头了啦，那你等一下哈，好了，你改完再看啦，这样很难看了。好了，
好 ，OK，
好，来那个家珍。
那么老师，我也是刚刚才搞 Table 2，然后我刚刚有发现我的第一个那个图就是。
那你现在程式可以跑一下吗？
是可以。
不能跑好看啊。
好。这样有画面吗？
有啊。
好，
就让它跑好看。
对，然后我图的话是让他去选，对。
哦，你把它改成同时都显示好了。
好，
好不好？
好，然后这是 Raw
One。Raw One 的标准差，等一下，平均数呢？平均数是没有，我跟你讲，你的命分别算 x 跟 y， 对不对？我上课有讲要算距离啊。
好，那这边我再改。
没关系，那你给它改成那个，我先看一下1D 的。
1D
的，对。好，那你这个平均数标准差那么小啊？你标准差用1好了，快，你这边用1吧，太小了。好，大概是，你这边，
我觉得我这边
也怪怪的。
对，
你自己再调了，1点多。好，你按 Raw 2，我看一下。你这应该变异数要是它的1.4倍。
对，我变异数那边应该有错。
应该也是不对啊。
对。
好吧，那你再去修吧。
好
了，就先这样了。
好，是。
所以你们的来先关起来，你们先退出分享。 就你们同学没有也还没有太差了，至少都有东西，都有东西。哎，我们上第3章讲到哪里？讲到第几页？泽成讲到哪里？
老师我看一下，
嗯，那下礼拜大家再报告一次，然后把你的电脑带来，然后把你的 PowerPoint 都准备好，可以吗？可以吗，同学？
可以。
可以。
可以
可以。
你们昨天有上蔡老师的课吗？
有。
有
是用线上的吗？还是
线上？
OK 好。哎，我昨天发讯息，为什么都没有人要理我啊？你们都不会自动自发，我想说，哦，我小白兔，我要看大白兔会不会反应，大白兔就说啊，我来看小熊会不会反应，我小熊会看大熊会不会反应。你们读不懂我的英文吗？就没有一个人要回答我啊，除了力宏以外。
我想说，
我想说什么
在另外一？个群组里已经有看回了。
谁有回？谁有回？力宏啊，是不是？
我有回啊。
我是又贴到范家版，你们才回，好不好？贪睡的时候没有人回啊，到底是怎样？我就搞不懂你们到底心里在想什么，还是说要叫你妈妈替你回？哎，我们第3章讲到哪里？哦，你们这个世代有时候很难沟通哦，你们问题越来越多了，我觉得。那你们将来怎么带学弟妹？奇怪了，你这些孩子很难沟通。哎，上到哪里了？快点，第几页啊？小白兔，我们上到第几页？
哦，老师，我有印象，好像是在第11页刚讲完的样子。
第11页啊。好
对，有印象。
，OK。好，我们休息5分钟再回来，我们50分回来。 等一下哦，稍待一下，老师马上回来。
对啊，你吃啊，你要钱我给你啊。我不要，吃就好了，我不要。我不知道。什么？有煮啊。
Okay, we like to back to our class. So, hold on. Let me share. Let me share my screen. So I think we run a little bit behind our schedule. So like to speed up a little bit. Okay, then, yeah, let me see how to share. Like to share my screen on my computer. Big data course, no, not this one. CD and D. and time series. Chapter 3. Okay. Page 11. Yeah, I'd like to see the full screen now. Full screen. Okay, so, okay, then we move to the page 11. So we have done, hold on, that's strange. How come? Okay, however. Why? Jesus. Why? It doesn't appear normally. Hold on. Yeah, let me. If I share the screen, no, I just skip out. Hold on. Don't want to do that. How can I skip out? Yeah, let me see. How can I? How can I terminate? How can I terminate? Like choose full screen, then that's strange. However, I don't like the presentation. 它要怎么样让它停掉？我不要用这种显示方式啊。看一下分享内容。我如何停止分享啊？我看。
老师，你要停止分享吗？
什么东西？
老师，你是要停止分享？
对啊，我现在要停止分享，我现在找不到那
按上面
有一个
就是老师原本按分享那边，
按下去以后，
他再按一次，
这样
它有个叉叉。
没有啊，就是没有这个，这版本是吐血，这到底是发生什么事啊？啊，你们现在还是有看到荧幕吗？
有看到
有啊，有
对呀，
看到荧幕
我现在没有办法停止分享，因为
啊。老师，你是不是按到投影幕就是放大的那个？你按 ESC。
等一下，我看一下。按 ESC 也没有办法，奇怪，我这是显进内容没有啊？我现在这就有点问题啊。这个谈电脑音效，我看一下背景，我现在停不下来，我现在要怎么样停呢？看一下浏览 Freelance Invision。我刚刚要求控制 ，OK， 好，我现在回来了，是不是？
对。
我刚刚分享我的，老师就跳出来了。
都跳出来，好 ，OK。所以说，我现在要等一下，我现在要分享，所以我这个程式有点怪，好，没关系。我现在分享要用我的 full screen， 等一下哈，因为我在我的电脑是正常的，所以说我用我的电脑的荧幕来分享。等一下，视窗来自相机的内容。视窗 ，OK， so I like to。有看到画面吗？有吧，应该有。有看到吗？
有看到。
Okay, sure. Okay, then we get on this version, right? Okay, so last time we addressed the AR1 process is we define the YT tail. That is used to describe the deviation from mean. That's YT minus mu. So where the size is used to denote the process offset, that is intercept. Process phi, this is autocorrelation coefficient, and YT minus 1, so that is an AR1. So we only have a correlation between YT and YT minus 1. So this is a series lag equal to 1. So we move to psi. So we just plumb it. We just plug the YT tail into the equation. So finally, the whole system can be turned into this equation, the YT tail equal to the phi YT minus 1 tail plus epsilon t. Then rationale. So why it is stationary as long as the phi we just keep just plugging by iteration by iteration. So keep doing that. Finally turn out to be the phi cubic YT minus 1, phi 2, epsilon t minus 1, t minus 2. The phi epsilon t minus 1, then and the epsilon t. If we keep doing that, there generate geometric series like a phi squared, phi cubic, phi quadratic, and so on and so forth. So as long as the phi constraint within the 1 and the minus 1, then that will be perfect. Then the whole system will converge. If you put the phi equal to the 0.9 or 0.95 or even some number smaller than 1.0, the whole series convergence, right? For the moment of an ARP process, look at this equation. On my left, this is the autocovariance. On my right is the autocorrelation. So you can see that there. On the left, this is gamma 0. Gamma 0, that means there's no system delay. So this is it reduced to sigma y squared. So there's no autocorrelation since the k is equal to 0. So that is a sigma epsilon squared, the epsilon corresponding to the random sequence or the y sequence. The gamma 1 is proportional to gamma 0, only we put the phi and pre-multiply by phi times gamma 0. So this is a phi sigma epsilon squared divided by 1 minus phi rho 1, and so on and so forth. 1 minus rho 1 and sigma the phi square, the phi cube until the phi k. So this is only AR1. So on my right, this is autocorrelation. So the rho 1 is autocorrelation function, which is defined the gamma 1 divided by gamma 0. So gamma 1 divided by gamma 0. So this divided by this, the gamma 1 divided by gamma 0. So going to be phi and the phi squared, phi cubic, phi quadratic until the phi k. So this is AR1, the moment of the ARP process. So so I think this result is quite understandable. So it has been elaborated in chapter 2 already. So we solve the equation for the root finding procedure and find what is the stationary region for the AR1 and AR2. So this is an AR2 process. And the YT tail equal to the phi 1 YT minus 1 and phi 2 YT minus 2. So remember, this is not Y, this is the YT tail. The YT tail represent the deviation from mean. So we move to the first two terms to the left-hand side. which can form the a polynomial times yt equals epsilon t. So I think it should be yt tail. Here it should be the yt tail. And by solving the equation or apply the jury's criteria conditions for AR2 system to be stationary, yeah, I understand. To be stationary, which can be found. The sigma, the absolute value of the phi2 got to be less than 1, so that is the must constrain between the 1 and -1, and phi2, phi1 plus phi1 must be less than 1, and the phi2 minus phi1 must be less than 1 as well. So finally, to form a triangle region for the feasibility for the stationarity region for AR2 process. Then the mean value of a stationary ARP process, yeah, can be seen. We directly put the yt in the expected value operation. So this is a phi plus a phi1 yt minus 1, phi2 t minus 2, plus a phi p t minus p plus the epsilon t. So expected value, since the psi is a constant, we take the expectation still equal to the psi, and expectation of the phi1 yt minus 1, the phi1 is a constant. So expected value of the yt minus 1, since it is stationary, we assume it is stationary ARP. So expected value yt minus 1 still equal to mu. So that is a phi1 mu 1, phi2 mu 2, phi3 mu 3 until the phi p mu, no, this is still phi p mu. So which can be collected into a summation. So summation j starting from 1 to p. So this is the phi j times mu. Expected value of epsilon t. Expected value of epsilon t. So why expected value of epsilon t disappears? 0.
有
Why? ？Why？ 0。小白兔。
我有听到。
OK， 0。那为什么 epsilon t 不见了？
因为它会趋近于0。
Yeah, okay. Expected value epsilon t is 0. That's great. So we got this equation, right? And mu and this one, we move to the. 你们大家可以看到我的游标吗？
可以。
Okay. So second term, move to the left-hand side. We factor out mu, so that is 1 minus summation phi j, right? And the right-hand side leave the psi on the right-hand side. So mu can be represented as psi divided by 1 minus summation phi j. So what is the implication? If this process is autocorrelated, what is going to happen? 安婷。安婷。
我有听到。
你知道我在问什么吗？你不知道我在问什么，对不对？我是说，假如说这个制程它是 autocorrelation 出现的话，那这个整个制程会跟原来的 IID 差别在哪里？因为我所有的假如是 IID， 我就没有这些 phi 了嘛。但是我有的 phi， 我假如有 autocorrelation， 就拿 AR1 好了。这边的 phi 是 0.2， 1减掉 0.2 就变 0.8。本来假如是 IID 的时候，它的制程平均会在 psi 这里， 那你现在又除了一个1减掉0.2、0.8，所以说它的自成平均会什么往上提嘛 ，right？对，这个是不是我上个礼拜有讲？我记得我有讲，对不对？有还是没有？安婷？
这有。
Okay,好。Then there are 3 cases in the following. If the phi is 0, then the whole system reduces into an SPC model. If the phi is equal to 1, so equal to 1, and that's going to be the random walk model, which is exploding. It totally so going to explode out, then if absolute value of phi is less than 1, then it decays exponentially. So it decays exponentially, that means the process is stationary. It is stationary. Okay. So then we talk about the mean of the process like this. The mu equal to the expected value of yt. So that is a psi divided by 1 minus phi. This is AR1 like this one. That equation comes from here. Then for an ARP process, the mu equal to the psi plus the summation of the phi j mu. So mu can be represented into this. So this is AR1, this is ARP. So based upon the ARP, the U-worker equation is available. So how can we have this equation? Let me see, like that. Yeah, like this. Let me see that. Our gamma k, gamma k, gamma k, phi1, phi2, U-worker equation, gamma k, phi1, gamma k minus 1, phi2, gamma k minus 2. Yeah, let me get that. Let me get that. Yeah, like this one. The equation gamma k equals phi1 gamma k minus 1, phi2 gamma k minus 2 until the phi p gamma k minus p. So the last equation is equal to 0 since there's a since the yt and the epsilon t hold on, expected value gamma k. Hold on, yeah, let me see that. There's only one remaining sigma k. Expected value. Hold on, equation 1. Yeah, let me see that. Equation 1. Like this. Yeah, like this. Like this. Equation 1 gamma k phi 1 gamma k minus 1 phi 2 gamma k minus 2 until the phi p gamma k minus p. This is the original equation. And okay, we move to here. Hold on, why there's a something? Hold on, let me check one more time. There's some missing. Yeah. Take the expected value. Yeah, I think we use this equation for sure. Yes. And k equal to 0, gamma k. So where does this come from? The strength from equation 1 k equal to 0. Expected value gamma k. Yeah, how come from this equation? Equation 1. Yeah, let me elaborate. This is a little bit different. Yeah, like this. Okay, from here. It comes from here, expected value. So So gamma k should be the t, the yt minus k. Okay, I'm sorry. This should be t minus k. This should be t minus k. This is typo. Since this from here. No, this is a k equal to 0. If k, this is t minus k. Should be t minus k. Gamma k. And since this expected value of this got to be equal to equal to 0, so there's a no shear term in common in the equation 1. So if it's set up that they're going to be in this 0 minus 1, this is phi 2 the same. So this equation is when the k equal to 0. Okay, so this should be gamma 0. This should be gamma 0. Then yes, the gamma 0 equal to blah blah blah, like this one, the gamma 0 phi 1, the phi 1 gamma 1 phi 2 gamma 2 phi p gamma 2, the gamma p things are in which case k equal to 0, so there's a shear term in common, so it reduces the sigma epsilon square. So this is a little bit different. This case is k equal to 0, and this case the k is not equal to 0. Right? Okay, back to the where we have. So this is your worker, remember. So the gamma k equal to that. This comes from the equation 1. Then if the gamma k divided by gamma 0, so gamma k divided by gamma 0 is which produce the rho k. So autocovariances are transformed into the autocorrelation. So this is ill worker for the version of the autocovariance. Then the second are the version of the autocorrelations, correlation function. So rho k equal phi 1, rho k minus 1, phi 2, rho k minus 2 until the phi p, rho k minus p. So example 3.4, pretend to your textbook as well. So this is a AR2. The YT, this is the phi, psi, phi 1, y minus 1, phi 2, y minus 2, plus the Y sequence. Then we let the YT tail equals the deviation from it. So the mean can be represented as the intercept, the psi, divided by 1 minus summation phi, 1 minus summation of the phi j. Since this is AR2, we put the phi 1 and phi 2 here. And for the sigma y square, that is a gamma 0, there's no system delay, no time lag. So it's let me see that. Do we derive the variances? Let me see. Yeah, exactly where we were in the last week. So sigma y square, if there's autocorrelation, that produce the variance equal to the sigma epsilon square divided by 1 minus summation phi j rho j. 1 minus summation phi j rho j. So this is 1 minus phi j rho j, like this. 1 minus phi 1 rho 1 minus phi 2 rho 2 as well. Okay, this is about the variance. So as can be seen from this equation, what do you observe? If there's a positive autocorrelation, what is going to happen with the autocorrelated process? 来，于晴。于晴。啊，于晴。
等我一下，会变大。
Yeah, So you can see, yeah, that's great. So you see the denominators is getting this positive correlated 1 minus positive number, so to inflate the variance. So inflate the variance, that means that if we construct the SPC model, which will be very difficult for the process engineer to monitor the process. 这样会造成什么后果？立宏，只要有正相关的时候，变因数变大，然后会造成什么样的后果？怎么会造成监控制程很困难？那为什么？来，立宏，
为什么？为什么？
老师上礼拜是不是有讲？看一下，假如说我们不把这个正相关考虑到管制图里面去，我们就会用。来，你们稍待一下。是你们的手机还是我的手机啊？OK, back to here。来，立宏看一下，最后它的变因数变大了。那假如说我还是没有察觉它有 auto correlation， 我用当初的 IID model 去建立管制图，我变因数变大了，代表我有很多的点会什么？超出我的管制界限。
对。
但是我的制程这些 phi 1 phi 2都是符合我们 stationary 的 condition， 都符合我们稳态的条件，代表制程是稳定，只是有 auto correlation。所以这个时候就有很多点会超出管制界限，超出管制界限，这个系统就会告诉制程人员说 ，OK， 制程不稳定，所以这是什么 false positive， 对不对？
对
，false positive 是什么？责成
行恶
啊？什么？
行恶
？Capture error。
行恶吗？行一还行二 ？false positive。
哦 ，false positive 是行一。
到底行一还行二？
应该是行一。
行一误差嘛 ，false 就是什么？它应该是好的产品，但是它被错认为是坏的产品嘛，对不对 ？false positive， 对吧 ？So there's a false alarm, there's a lot of false alarm， 它会造成我们的这个客户，这个制程工程师很难来监控这个程序嘛，对不对？这就造成很多 false positive， 就是所谓的 false alarms。Okay, for k equal to 1, then if k row 2, k equal to 1, row 1, phi 1, row 0. So what is the value of the row 0? 家珍，
在
row 0是等于多少？有没有人要替他回答呢？快点啊！来，那个大白兔，你帮他回答。还是小白兔回答？
等于1吗？
当然等于，为什么等于1？是谁回答的？家珍啊？
2例。
是谁回答的？
啊，力宏。
谁啦？哎，你声音很小，是谁啦？
力宏。
好，来，你说为什么等于1？
因为第12页，第12页如果 rho 等于0的话，就应该是等于伽马0除以伽马0，所以 phi 就等于1啊。
Yeah， 当然，就因为它自我相关是跟自己嘛，它当然是100%了。Okay. So this is a row 1, phi 1 plus a phi 2. Then, what is the value of the row when k equal to 1? What is the value of the row minus 1? 来继续问力宏好了，这边我们 k 带1的时候，那我这边第二项会是 phi 2 row 负1嘛，对不对 ？row 负1等于什么？
不会啊。
哦，不会啊，好来，那我啊
1/1吗？
不是，row 负1跟 row 1是一样的，一个是我的自我相关，我是跟前面比较前一期，一个是跟后一期，所以基本上只要在 AR1，不论是我跟前面比跟后面比，等于是说我自我相关是我跟明天比，今天跟明天比，跟今天跟昨天比是一样的，所以说 row 负1就等于 row 1啊。Okay, so we have here. We have phi 1, phi 2, row 1, right? Okay. Then if we put the k equal to 2, the row 2 equal to the phi 1, row 1, phi 2, row 0. So row 0 is equal to 1. Right? So we have the second equation. So we have equation 1 and the equation 2. So row 1, row 2. Phi 1, phi 2. So we're going to solve. As long as we have the value for row 1 and row 2, we would like to estimate what is the value for phi 1 and phi 2. We're solving the simultaneous equation to obtain the phi 1 and phi 2 in this equation. So that is easy. So which can be represented. This is x equal to the theta times the x. Then we just use the inverse of the matrix and to solve the simultaneous equation to obtain this. Then if the phi can be estimated and the phi can be estimated, so the phi 1 hat is equal to the R1, the phi 2 and then once while, hold on, let me see that. And the phi 2 equal to R2. So the phi 1 and phi 2 can be estimated. Then we have a R1 and R2, or conversely, which can be estimated in the other way. So let me see that. So the phi 1 and phi 2 can be simultaneously solved in terms of the R1 and R2, and the row put into that, and phi 1 and phi 2 can be estimated. So how can we get the R1 and R2 from the sample autocorrelation function? Then generally, so generally for an ARP process, the Ill-Walker equations are like this: phi 1, phi 2 until the phi p, and well, if you like to solve the phi are unknowns to be solved, and this is the equation, the row 1, row 2 to row p, so which can be represented into that like this. That represent the simultaneous equation into the matrix form. So P equal to 1, row 2 until the P minus 1. 1, yeah, let me see. P Let me see that. This is row 1, p minus 1. Yeah, the 1, row 1, row 2 until p minus 1. And the row 1, 1, row 1, 1, row 1, row 2 until p minus 2. So we just keep moving. The one that keep moving on the diagonal. So p equal to that. Then if the p can be represented into this matrix form, so the row equal to the p times the row times phi. I'm sorry, on the right hand side, the phi 1, phi 2 until the phi p. So the p equal to p phi equal to the row. So since we like to solve the root of phi, so if the p is invertible, if the matrix p is non-singular, so its inverse matrix exists, then the phi can be solved, can be represented as the p minus 1, the inverse of the matrix times row. So solution to the ill-Walker equation of the ARP, this ill-Walker equation can be represented as a phi equal to p of inverse times the row. So ACF, autocorrelation function, decays exponentially or as a sine wave if the ARP is present. Okay, so as long as the ARP process is stationary, then the autocorrelation function decays exponentially, or it going to converges. It converges as a sine wave. It could be either way. Then we finish introducing the first component of the Riemann model. Then we move to the second component, which is the moving average process. So a process can be represented instead of a sequence of the random shock, that is epsilon t's entering the system. So it is the so-called the moving average MA process. So we have an AR, then we have an MA. So this is MAQ. So like before, the YT minus mu is represented as a YT tail. Then, let me see that. Hold on, I can see. Okay, this is mu. Okay. This is YT tail. Okay. So move to the left hand side, YT minus mu, the YT tail, and we have a -1 theta epsilon t minus 1, minus theta 2 epsilon t minus 2, minus theta q epsilon t minus q, and plus the last one. This is a random shock at the present t. Then we rearrange all the term on the right hand side. So YT tail equal to the 1, factor out the epsilon c. So it can be represented as a C polynomial. So 1 minus theta 1, backwash operator -1, minus theta 2, the backwash operator -2, and so on and so forth. So yeah, I can see the A polynomial, in which case in here is a 1, right? Since a constant, so since the A polynomial is constant, so moving average process is always stationary. So the 1 times YT tail equal to the C polynomial times epsilon c. So you can see that this is a C polynomial. So there's two definition I would like to introduce. The first one, the MA, this moving average process are always stationary. Why? This moving average, that since the A polynomial always stable, since always a 1, this is a hidden one. So we just put it in intentionally. Actually, it doesn't exist at all. We just intentionally put the 1 here. Actually, which is constant. So the moving average is always stationary since the A polynomial is a constant. A polynomial is simply equal to 1. Then AR processes are always invertible since the C polynomial is simply equal to 1. We call it invertibility. So which can be inverted. C polynomial, let me see the AR. Yeah, let me say the AR process. We move to like this. Let me see. Okay, look at this. This is an AR process. The C polynomial always equal to 1 times epsilon t. So the AR always invertible since the C polynomial is simply equal to 1. Different. So remember, the A polynomial is simply equal to 1. So in the MA process always stationary. On the contrary, AR process always invertible since the C polynomial in the AR process is simply equal to 1. So we define what is the invertibility about the C polynomial. If a process can be written in the following format, the YT tail equal to the pi 1 YT minus 1 tail, pi 2 T minus tail, pi 3 T minus 3 tail, and so on and so forth, plus the epsilon t. So where the sum on the right converges for given pi 1, pi 2, pi 3, and so on and so forth, then, so remember, the YT must represent it in a linear combination in terms of the Y of the different time lag. The YT as a combination of the T minus 1, T minus 2, T minus 3, and so on and so forth. If it is represented in the combination of the of itself of a different time lag, then it's called an invertible process. So where the sum the right convert if this is so how can we make this convergence? Pi 1, pi 2, pi 3. If the pi, the series of pi, is exponentially decaying, then it must be convergence. If pi is decreasing, exponentially decreasing, and the YT, so process is invertible. It's invertible. So based upon this idea, so epsilon t, so we move to a C polynomial to the left-hand side. So epsilon t can be represented as a YT tail divided by C polynomial. So if the root of the C polynomial is strictly outside the unit circle, C polynomial is stable, then the whole MA process, moving average process, is invertible. So the invertibility of the moving average strongly depend. So purely depends on the root of the C polynomial. Okay. So AR processes are always invertible since the C is simply equal to 1. So it is called the invertible process. It can be represented as this one, and the pi is exponentially decreasing. So if the effects of the previous observation on the current observation is decreasing according to the age, then that is we call the invertibility. Okay, we stop here for a while. Any question? 来，力宏，来有没有问题？
其实我这个我听不到，
听不懂？你听不到还是听不懂？
我听不懂。
哦，听不懂。OK， 来，小白兔，有没有问题？
嗯
说话，
嗯，
懂就懂，不懂就不懂啊。
哦，懂不懂？有一点不太懂。
OK， 好，来，那志荣呢？
还在思考，没有听得很懂。
来 ，OK， 来，老师讲一下。我们从 AR 开始。大白兔，你懂吗？
不懂。
不懂，真的吗？你不是很聪明？来看一下啊、我们当初是不是讲过 A polynomial？A polynomial 它的 stable，来看一下。看哪里？哦，对，这个嘛，对不对 ？AR1、AR2的时候是不是讲过它的 stationary condition？它的有两种方法，有一个是直接解根，对不对？另外一种是用 Jury's criteria condition，就是大家要交的作业嘛，对不对？那解 AR2 最后解出来这个有没有？它是针对什么？这个移过去，这边是不是 A polynomial？我们求根的话，希望 phi1 跟 phi2，它的根是什么？带过去 operator 就是 q minus 1，对不对？这边是一次方，这边是二次方，所以就是二次方跟解根嘛。最后解出来的这个条件，让 AR2 它可以进行 stationary 稳态的，是不是刚好是在这个三角形，对吧？是不是？在那个三角形好，那这个是等一下老师才定义什么叫做 stationary。那现在这是 AR， 现在回到 MA 了。MA 又不一样了 ，MA 它定义就有点不太一样，像这样 ，MA 的意思就是说我的制程它是过去的 random shock 的一个累积，就等于是制程会受到过去的误差，但是在不同时期的误差的累积的总和，对于我的制程的影响，对吧？这时候本身就跟自我相关不一样。假如是这种制程，我们就叫做 MA process 哦。先有厘清这样的一个概念。好，那现在我们把它这个 MA process 就变成 YT 等于 C polynomial 乘上 epsilon t。那这时候我们先讲 stationary。stationary 我们当初在 AR 讲了 stationary 的时候，要看 A polynomial 的根嘛，对不对？但是这里的 A polynomial 是什么？一嘛，常数，所以它自动你根本不用考虑，只要是 MA process， 它的 A polynomial 就是一。假如 A polynomial 一它是稳定，它一当然稳定，它不会乱动啊。那请问 MA process 是不是 stationary？ 当然是啊，因为它的 A 就是常数嘛，懂意思吗？就是这样的意思。哦，然后再来，好啦，那这个是 MA process， 它一定是这个不是对不起，这个 MA process 它一定 stationary。那我们现在要讨论这个叫做 invertibility， 叫做可逆性，可逆性好了，我也不知道怎么翻译。好，那要看 C polynomial 嘛，对不对？这个 C polynomial， 假如说它整个所谓的 invertibility 可逆性，它的这个 y 它可以写成这个样的形态 ，y 是等于是过去的制程的怎么讲？它制成的观察值的一个线性组合，而且这些拍啊，它是越来越小。我这边讲说是有什么这 decreasing according to the age， 对不对？只要可以变成这样，所以这个地方就发现，我们为了要它符合这个条件，那这个 C polynomial 一定要怎么样？这个 C 对不起，我现在要看什么 C polynomial 这里好。那这个 C polynomial 这个根啊，就是 Q 减1，它一定要在 unit circle 之外，对不对？ 就跟 A polynomial 一样。所以我们这个 C polynomial 只要稳定的话，只要它是 stable 的话，它整个 MA process 就是什么 invertible。所以说它的 invertibility 是跟什么有关？跟 C 有关，跟 C 有关。好，那所以说我们就说我们的 MA process 什么时候是 stationary 是 invertible 呢？就是 C 的 polynomial 要 stable。C 的 polynomial 要 stable， 我们就是解这个根。好，那这个我们再讲一遍 ，MA process 假如它是 invertible， 就要看 C 的根，对吧？好，那现在问题来了，我们把这个概念又回到 AR process。AR process 的 C polynomial 是什么？AR process 的 C polynomial 是什么？1啊，对不对？AR 里面只有 A polynomial， 它没有 C polynomial， 所以 AR process 里面它的 C polynomial 是等于1，所以说 AR process 永远是什么 invertible， 因为它永远可以去写成这个样子，变这个样子。OK， 所以说我们昨天就得到一个总结，我们来念一下 ：If the effect of the previous observation on the current one is decreasing according to age, then invertibility holds。所以说 A polynomial， 对不对 ？AR process 永远是怎么样 ？invertible。MA process 永远是 stationary。我再讲一遍 ，AR process 永远 invertible，MA process 永远是 stationary。按照这个定义来讲 ，OK。Since a process invertible if C is stable, the root was solving the root of the C polynomial. So all AR processes are invertible. Since O is invertible since C is equal to 1. Clearly, the AR process is invertible because it can be written as the equation, the double asterisk, like this one. So like clearly AR and ARP is invertible because it can be written like phi1, phi2, phi3, and so on and so forth. It's a less than P. This is a phi j greater than P. Oh, 0. Of course, this is decreasing for sure. It must be stopped. It must be stopped, right? Then, we define the stationarity is the inference of the previous term on inference of the previous term on the current observation decrease with time. So the previous noise term on the current observation. The invertibility is the inference of the previous observation on the current observation decreases with age. Okay, so let me see that. The first one. So you can derive the AR1 and MA1. You understand why this is true. Let me say it again. Stationary dictates the inference of previous noise term on the current Y decreases with age. On the contrary, invertibility, the inference of the previous observation on the current observation decreases with age. So then we back to the moving average process. Yeah, we'll take a break. Please return here until 11. We'll take a break. 我们休息一下。
好。
OK， 等一下，我去倒个水，马上回来。OK， 来，等一下 ，back to here，back to here。Okay. So for the moving area autocovariance and autocorrelation， 能听到声音吗？有画面吗？
有都有。
听到声音有画面。
Okay. So MAQ, the model, we take the expectation. Take the expectation like this. Okay, this is RK. No, gamma K take the expectation. This is a MA process. See that. Okay, I use this, and this is the origin. I'm sorry. How come? Okay, then this is original. This is original. Then take the RK, and there's a K time lag, T minus K and T. This is time lag. Minus theta 1 epsilon T minus K minus and so on. So take expectation. So after arrangement, the gamma K can be computed. If the K is greater than Q, the Q is the order of the moving areas. If this is a greater one, then there's no autocovariance for sure. Then, however, if is less than or equal to Q, like a K is equal to 1, 2, 3 until Q, right here, then the gamma K can be computed as this. Okay, the sigma epsilon E is the variance of the Y noises, the Y sequence, and there's a minor, so which can be confirmed. It's just do the multiplication and takes expectation for sure. Then this is gamma K. So if we place the K to 0, then gamma 0 equal to that. The gamma 0 equal to the sigma Y squared for sure. Where does this come from? From here. Right? So you can see that if the K 0, K is the 0. Okay, look at if the K is equal to 0, let me see that. Okay. Gamma Z, let me see that. K equal to the minus, there's no theta 1, 0. Okay. So K equal to 0, theta 0. This is no such term. No, since this is no such, and this is theta 1. How come this? Where does this come from? Let me see that. K. Okay, then. So let me see that. If K equal to 0, this is theta K. So theta K times the theta K, the theta K squared, and the theta 2 K equal to theta 2, and the theta 2 squared, and the theta 1, the theta 1 squared, and minus theta. Where is the theta K? Theta 0. Why is equal to 1? How come? Yeah, let me see that theta 1. Where is theta 1? Let me see that. Theta 0. Nice. Where is theta 1? I don't know. If K equal to 0, how come? Theta Q, theta 2, theta 1 minus theta K. Yeah, let me see that if it is possible, it's greater than that. Why this is true? Why this is true? Okay, then. I think hold on. It should come from here. Yeah, theta K, like this. Yeah, it's a K equal to 0. How should I? Variance is 1. The 1 is come from here. Hold on. The 1 come from here. So this is a 1, right? This is a 1. And this is minus theta q. This is minus theta q minus 1. The minus theta 2. This is minus theta 1, right? So if we do if the gamma 0, we like to see the variance of yt, right? I'm sorry. It's yt. Is this mode? So if this move to that is equal to the expected value. I'm sorry. This yt tail. If the mu move to the left hand side, the yt tail square. Since the mean is equal to 0, since the mu is already moved to that, the yt tail square, right? So is this multiplied this? So expected value of this multiplied this after modification, so epsilon t times epsilon t is a 1. So going to be the 1 plus the minus the minus theta q times the minus theta q is the minus q squared plus. And minus t minus 2 minus t minus 2, so blah blah blah, and plus the theta 2 squared plus the theta 1 squared, and the collect them all together times epsilon t, the sigma epsilon squared. This is where does it come from, right? So from here, this is theta 0 in here. This is this should be the theta 0, and this is theta 1, theta 2, minus theta 1, minus theta 2, minus theta q. However, this is 1 here. This is 1 here. This is right here. 1 right here, right? Finally, we have a 1 right here. 1 plus theta 1 square plus theta 2 square plus the theta q square. Okay, so if the k is greater than q, this is 0 for sure. The gamma k, since the rho k is defined as the gamma k divided by gamma 0, right? So for sure. And the gamma k divided by gamma 0, so this time divided by this. This is minus k plus the theta 1 k plus 1 and so on and so forth, divided by this. As long as the k is less than or equal to q, right? Is that clear? Is there any question? No? Then we take a look at the moving average one. I use a different ladder. I think I use this. Okay. Like this. Okay. Then the yt equal to the mu theta 1. So it is theta 0 is equal to 1 for sure. And if we represent as a yt tail, move the mu to the left hand side. The yt tail equal to this one. This is a 1 factor of 1 minus theta 1 backward operator. So this is our C polynomial. A C polynomial. Okay. Then the variability. So it won't matter as yt tail equal to the variance of the variance of the yt tail equal variance of yt. It won't matter since the only difference is only a constant right here. So this is gamma 0, then represent as 1 plus a theta 1 squared sigma epsilon squared. Where does this come from? Right here. gamma 0, the 1 minus theta 1, 0, and the sigma epsilon squared. Okay, then if there's only it has a value as long as the k equal to 1. If it is greater than this equal to 0, since this moving average 1, the moving average process of order 1. So this is autocovariance. This is autocorrelation. It's greater than 1. Of course, this is 0 for sure. Is equal to 1. This is minus theta 1 divided by 1 plus theta 1 squared. That's right. 1 plus theta 1 squared minus theta 1. Okay. This is moving average 2 of order 2. Like before, move this to the left hand side. The y minus means this is yt tail, and we just rearrange all together this three term on the right. The factor out epsilon t that produces 1 minus theta 1, 1 minus theta 1 backwash operator epsilon t, and the 1 minus theta 2 the backwash operator minus 2 right here. This is time lag. So expected value of the mu, the yt equal to mu, since epsilon t minus 1, epsilon t minus 3, and epsilon the y sequence and also independent. And the variance of the yt of this is 1 plus the theta 1 squared. It's a theta 2 1 squared, since there's a no covariance right here, since so between the epsilon t of the different time lag, they are IID. So this, I use a different like this, this, and this. These three are I by D. Since they are independent, so of course when we take this directly 1, and it won't matter. It's a plus or minus. It won't matter. So the this is theta 1 squared. This is theta 2 squared. Okay. Like before, if the k is greater than 2, then of course 0. Since this is an order of 2, then is a k equal to 1 right here. K equal to 1. Like here, k equal to 1. Let me see that. Which should, I'm sorry. If k equal to 1, this should be, since the AR2, okay, gamma 1, okay. Let me see that gamma 1, this is a minus theta 1 plus the theta 1, theta 2, since the remaining going to be now. So it's a minus theta 1, and the theta 1, theta 2, okay? If the k equal to 2, yeah, you directly use this, the minus theta 2, the theta 1, theta 3. So since we have a no theta 3, so don't worry about that. There's only one term, minus theta 1. So this is minus theta 1. No, I'm sorry. This is a minus theta k, the minus theta 2. This right here, the theta 2 times this. So that then this is quite straightforward. From the gamma k transform into the rho k. This is gamma k divided by the gamma 0. So this is a k greater than 2. Of course, this is 0 for sure. If the k is equal to 1, then yeah, this divided by this. The minus theta 1, theta 2 divided by 1 plus theta 1, theta 2, and so on and so forth. And k equal to minus theta 2 divided by 1 plus theta 1 squared plus the theta 2 squared. The k equal to 2. Right? Quite straightforward. Any question? No? Okay, great. Stop here. 家珍 家珍，
哎，有，
这里应该没问题吧？应该蛮直接的。
嗯，
好，那力宏，
可以。
好，然后小白兔、
可以，
大白兔、
可以，
小熊、
可以，
大熊。
可以。
Okay. Then we move. We proceed to the not stability condition, invertibility condition. Yeah, let me see that. So try to the dual condition. So talk about the invertibility condition. Invertibility condition. 哎，泽产，喂，
嘿，
泽产，
嘿，
那个有没有那种笔电哈？那个直接可以用笔写在荧幕上的，有没有这种笔电？
有。
哦，假如说将来还有设备费，就去买一个那种，有没有？直接老师在那个，
荧幕上可以直接写字的。
对对对，这样我就不
好
用用那个滑鼠这边弄，真的很痛苦。
好，
OK，好，就是有一种什么变形金刚，是不是？就是说，
微软的
对
Surface Pro
哦，OK，那个品质怎么样？还可以吧？
很多老师都在用。
哦，真的好啊。那看力宏，可能你找到资讯再给学弟妹一下，让他们去survey一下，好不好？
好，
它是微软的出的笔电，是不是？
对，
那它的笔电的功能好不好啊？就是
笔电。
就是纯笔电嘛，哈。OK。
对，可是它没有那么厉害，它不能跑，不一定跑那个很高阶的 Python 或跑要打电动不一定可以打，可是一般的都没有问题。
哦，好啊，没关系啦。那个泽成你就帮忙survey 一下，到底是哪一个厂牌，每一种功能都可以兼具，好不好 ？OK。
好。
OK，好。Then back to here, then this we talk about this polynomial C polynomial. C polynomial got to be stable. Got to be stable. Got to be stable. And then the rule finding. So as before, this is like a AR2, right? Pretty similar in AR2 in the A polynomial. Then, however, this theta, 1 minus theta 1 minus theta 2. So we're going to find what is the root. This is referred to the root finding procedure. Then the root finding, so the backwash operator, the root got to be strictly outside the unit circle, right? Strictly outside the unit circle. So it can be found. It can be found. The theta 1, the theta 1 plus theta 2 got to be less than 1, theta 1 minus theta, the less than 1, and or the absolute value of theta 2 less than 1. So this can be done by root finding procedure or jury's criteria, like we did last week. Right? Only. So what is a feasibility region? The feasibility region is like the triangle, right? Like a triangle, like this one, the last one. So in which case, the horizontal going to be the theta 1, and this is going to be the theta 2, right? Within this region, like we did before, right? Okay, now. Then for now, we already know what is the AR, what is the MA. Now, how about that? We're going to combine them together. So called the ARMA model. There's the two parameter P and Q. Okay, don't confuse with the Q. The Q is not equal to the backwash operator. No. Okay, the Q is the order of the MA. So in the textbook, in the textbook, they use B, backwash operator, And the forward shear operator in the textbook, you use forward shear operator, F. Okay. So that don't get confused. So a model may contain both the AR and MA component. So on the left-hand side, this is yeah, like okay, like this. We move this to the left-hand side to form the A polynomial for sure. And also use a YT tail, YT tail. The YT tail, as defined before, is a YT. Things up. We also talk about the stationary. So this is deviation from mean. Then this is a polynomial for sure. And on the right-hand side, this is the accumulation of the path arrow and the current. So this is current arrow, this is path arrow. Collect them together, 1 minus theta 1 minus theta 2 until theta k. So this is C polynomial times epsilon t. So collectively, we arrange all the terms, the A times YT tail times is equal to C epsilon t. So conclusion is AR MA PQ process is stationary. It talk about stationary, or we talk about A polynomial. The root of the A polynomial is stable. We talk about the ARMA model is invertible. We talk about the C polynomial. The root of the C polynomial got to be stable. That's it. So stationarity, that is A. Invertibility is about C. Okay. So autocorrelation and autocovariance are getting a little bit fuzzy, a little bit clumsy. So we multiply the asterisk by YT minus K tail and take expectation. Like this. We take this, and this is a ARMR PQ, and the time we multiply the YT T minus K tail and take the expectation, then which produce and take expectation like this. Wow, this is really clumsy. Really clumsy. So gamma K equals phi 1, gamma K1, phi P until the phi P gamma K P. Yeah, this is like a cross correlation. Gamma Y epsilon K minus the theta 1, gamma Y epsilon K minus 1. This is the order until the minus theta Q, the gamma Y epsilon, the K minus Q. This is order. Okay, this is the order. This is the order. This is the order. No, this is too dark. I like use a different. I think that would be greater. Okay. Then this if the K is greater than 1. If the K is greater than 1, there's no such terms in common. If the K is equal to 1, yeah, let me see that. Like this. Gamma, this is Y and epsilon. That is talk about what is a Y is a AR MA PQ. And this is a y, yt, and the epsilon is about the k, the k. So the y, you can see that this is about k separation. So this is t, and this is t minus k. This is where does it come from? About the k. This is about the k. K different. The k time lag is between the t minus k and t. So you can see that if the k is equal to 0, since it got to be non-zero, right? The k equal to 0, this is yt and epsilon t. There's a shear. There's a shear term in common for sure. Of course, this is non-zero. If the k is greater than 0, wow, there's no shear term in common. Of course, this is 0. 然后听一下这里，大白兔，你知道我在讲什么吗？大白兔，快点，
是，
懂不懂？
懂。
真的吗？你讲给我听，为什么上面是0，上面是0，下面不是0？
因为当 k 等于0的时候带进。
为什么？因为来，我讲一下，来看一下大白兔，来大家都听一下哦。k 大于0，k 大于0，比如说我今天是 yt 减1，对不对 ？epsilon t。那我这边来注意一下，我这边 yt 减1，这边是 yt 减1跟 yt。请问，那我最多这边是 yt， 那有没有另外一个 yt 项？没有啊。因为这是 yt 减1，它的最接近现在的这个 term 是 epsilon t 减1，那 epsilon t 跟 epsilon t 减1同样是 white noise， 但是在不同的时间，所以说它的 covariance 是等于0，所以它没有 shear term in common， 其他全部都是，比如说都更早，比如 t 减1、t 减2、t 减3，就跟 epsilon t 它一定是什么？它一定是什么 independent， 一定是 covariance 等于0，所以这个当然是等于0。好，假如是 k 等于0的话，这边至少有一个 term 是什么？有一个 term 是相同的。为什么？这边是，假如是来看一下 k 等于0，这边是 yt 跟 epsilon t， 看一下，yt 这边至少有一个 term 怎样？是 epsilon t， 对不对？这边也有一个 epsilon t， 相乘起来叫 epsilon t 的平方，期望值就是什么 sigma epsilon 平方，它一定是什么？它一定会至少有一个 term 是什么？非零。看到没有？我看到，这边是 yt， 只要是这边是0 ，yt 跳的话，只要是 k 等于0，看一下这里，这是 yt 啊，这边是变成这样，我至少有个 term 跟它是什么 in common， 一乘起来是 epsilon t 的平方，那期望值的 epsilon t 的平方，小白兔，这等于什么？
西格玛epsilon
等于 sigma
sigma 1的平
epsilon 的平方。对啊，没错啊，对不对 ？OK， 好，所以它一定会有一个什么 non-zero， 就等于什么？这里，知道了吧 ？OK，then， then we have a yield worker. This is a yield worker. The yield worker equation. Of course, the k gotta be good. This is greater than the k or equal to 1, and this is a yield worker equation. This is the autocovariance. This is autocorrelation yield worker, and apart from the first Q, this is k is 1, 2, Q. Okay, and ARMA has autocorrelation. ARMA has a ACF autocorrelation function that resemble of an ARP. Yeah, of course, this is as long as. So this is first Q. is a greater than apart from the first Q, starting from the first Q, the armor system has this behave quite similar to the ARP, except the first Q legs. In addition, from here, they do not resemble. And if it is a case is greater than Q plus 1, then it's a yield worker. The yield worker is the same as the AR. The same as AR, right? The same as AR. So from this understanding, it is obvious if the case is greater than, in addition to first Q lag, the behavior of the autocorrelation function will pretty similar to an ARP, since they have the same yield worker equation. Okay, done. So like ARMA 11, then this is P equal to 1, Q equal to 1. Okay, we already represent as a tail right here. And this move to the left-hand side, this is AR. Collect this two as a MA. So gamma 0 is a YT tail, YT times multiply this. Gamma 0, YT. Yes. So gamma 0, this is YT, the YT times the theta 1, YT minus 1, theta 2 minus theta 1, epsilon T, and epsilon T. So this time this is a phi 1, YT minus 1, this is gamma 1, YT times the theta 1. Hold on. Okay. So factor out theta 1, the minus theta 1, and the YT and I'm sorry, YT and epsilon T minus 1. So this is time lag. This is time lag. The T minus 1 minus T is equal to minus 1. The lag is minus 1. Okay. And the YT times the epsilon T. YT times epsilon T, yeah, let me see that. The YT is equal to that times epsilon T. There's only one shear term in common, the sigma epsilon squared. Okay, this equation double asterisk. Then gamma 2, this is gamma 1, this is gamma 0, and YT tail, YT minus 1 tail. So that is YT equal to that. Copy from the original equation times the YT minus 1. Then this move to this one. Okay, T minus 1, T minus 1, the phi 1 gamma 0, and T minus 1. Yeah, no, I'm sorry. The T minus 1 is minus theta. Yeah, let me see that. Okay, T minus 1 minus theta. So the minus, this is minus theta 1 sigma epsilon squared. Okay, so the T minus 1 is right here. This only have a one shear term sigma epsilon, the sigma T minus 1. So sigma T minus 1. So we got a so the sigma T minus 1 squared. Expected value of that is the sigma epsilon squared. And the last one, epsilon T and the YT minus 1. This is no shear term in common. So this is 0. Plus 0. Okay, that. So this is gamma 1. The gamma 2. So this is YT tail times the YT minus 2 tail. So this is YT times this one. And this time, this is the theta 1 gamma, the gamma 1, since T minus 1, T minus 2 minus T minus 1 is a gamma 1. This is 1 right here. And epsilon T minus 1, T minus 2, no shear term in common, plus 0. And last one, epsilon t times the yt minus 2, no shear term in common. Look at that, the Q. This is, okay. The Q is equal to 1. So look at the first Q plus 1 leg. Q equal to 1, Q plus 1 is 2. We have a 2 leg. As long as the first Q K is greater than. Yeah, excuse me. Yeah, excuse me. So I'll be back. Hold on. Let me have this some urgent. Yeah, hold on. Yeah, don't worry about that. Okay, then the K as long as the K is greater than 2, so see that. Let me finish this. So this is a starting. Hold on， 我在上课，对，上课不要再吵。Then, I'm sorry. So you can see that this is starting to the 2, the gamma 2. In addition, the first leg, there's a something. Look at that first. Apart from the first Q leg in here, in which case, in here this Q is equal to 1. So in addition to this, the gamma 1, this is a something. Actually, there's no formula for such as autocovariance. Then greater than Q equal to 1, starting from 2, 3, 4, and gamma K. So this is the theta 1, gamma 1. From the gamma 3 is this phi 1 square. This is gamma 1. The gamma 1, or something like that. So the following autocovariance going to follow the ARP process like this. The phi 1 gamma 1, and this is phi 1 gamma 2 until the phi 1 gamma k minus 1. So actually this is autocorrelation of the ARP. Apart from the first k equal to 1. So in addition to that, the remaining going to follow the ARP. So this example explains why this statement is true. This statement is true. Okay. Okay, then to find what is that? Why this is true? This is -1. This is quite strange. So this is gamma y epsilon. This is -1. So you can see that this is -1. So the time of the second term gotta be a 1 time lag removed from its position. So this is the T. So the previous one, so the next one should be the 1 the 1 time lag before the current time. The current time got to be t plus 1. So why this is true? T plus 1 epsilon t. So which can be solved like this. How this is true? So t plus 1 times epsilon t. Wow, this is quite messy. I'm sorry. Okay, let me see that. This is t plus 1. Okay, so they're going to be t. So those are going to be t. So going to be the t plus 1, right? So this is yt plus 1. I'm sorry, it's kind of messy. T plus times epsilon t, I'm sorry. Okay. We're going to times epsilon t. Okay. This going to be multiplied this. So shear common epsilon t. Yeah, I'm going crazy. Epsilon t is right here. Theta 1. I'm sorry. Yeah, this is a minus theta 1 here. We have a theta 1. So we have a theta 1, the minus theta 1 here. So if the phi 1, yeah, let me see that phi. Since yeah, since epsilon t times theta 1 y theta 1 times phi 1 yt tail. So there's a shear common in epsilon t. So this is a phi 1 for sure. Okay. Phi 1 right here. Phi 1 right here. And this is the phi 1 come from here, the epsilon t and the yt. The minus theta 1 come from the yt times yt here. The minus theta 1 come from this term. All right. So we have this. The combine them together as the triple asterisk. So solving 1, 2, 3. This is 3. This is 2. This is 2, and where is the 1? This is a 1. Where is the 1? There's a 1 right here together. So we can obtain the gamma 0. This is a little bit clumsy. So solving these 3 equations to get the autocovariance. No, this is with time lag 0, and this is gamma 1. And yeah, let me see that this 1 starting gamma 2 is going to be the gamma this theta 1, the gamma t minus 1 as long as the k is greater than 2, and we decay for the k is greater than or equal to 2, and phi 1 this is gamma 1 divided by gamma 0. The phi 2 this is phi 1 divided by rho the phi 1 rho 1. And the phi 2 rho 2 and so on and so forth. Okay, this is only one this in addition to this time, the remaining going to be follow AR1 for sure. Okay. Okay, then. Okay, I'll stop here. I think this is good enough for today. So going to proceed 3.4 next week. We're going to talk about as long when the armor is not stationary, what are we going to do? What are we going to do? Then we're going to take the difference. We're going to take the difference data. DATA, to make it stationary. So what kind of measure going to take? Okay, then. So I think. Hold on. Stop here before we going to do that. Okay, everybody sign out here. 你在这边这边再帮老师再签到一次，等于签退了，好不好？帮老师签退，就代表说我们时间都是上到组的，这边帮我签退一下，快点。Hello。 Okay, so that. So next week, first hour, we're going to have our 10 project demonstration. So we're going to present how you implement the program, and you're going to show. So you're going to show your program, the online demonstration, and also we request you to make the PowerPoint. What is the summary of your finding, and how can you to emulate, to regenerate, reproduce those numbers from the paper? Okay, so I see you next week. Thank you.
那个老师，
怎样？
可不可以请您把那个录影开放啊？就是我
可以啊，
们可以
可以啊。我会那个我等一下就会把录影的那个档案，我的连接我会放到那个 i 学院去。对。
哦，好，谢谢谢谢。
Okay. Is there any question? No. Any question so far? 好了，那个你们不要太晚回学校，你们有一些都还在台中，你们要不要早一点回来？不要明天早上再赶。我是觉得这个没有必要拖到最后1分钟了，该回到学校就回到学校来。Okay, see you. So see you next week. Bye bye.
拜
拜拜。
拜拜。
谢老师。
谢谢老师。